Quick experiment. You want to know your average morning commute, so you time it, but only on, 6 mornings? 21 minutes, 26, 23, 28, 24, 22. Now somebody asks, so what's a reasonable range for your true average? And you realize you don't even know how spread out your commute is.
Right, and that's the gap from last time. In Lecture 14, we built confidence intervals, but we cheated a little. We pretended we knew sigma, the true spread of the population, handed to us on a plate.
And in real life, nobody hands it to you. So this is week 4, lecture 15. What do you do when sigma is unknown? We'll fix the interval for a mean, then do the same trick for a proportion, like that poll, and even for a variance. Let's go.
So the honest situation, we don't know sigma. What's the move?
We estimate it from the very same sample. The sample standard deviation, little s, that's just the square root of the sample variance, s squared, which averages the squared distances from x bar, dividing by n-1.
And we can trust s for the same reason we trust x bar. As the sample grows, s squared marches toward the true sigma squared. So s is a fair stand-in for sigma.
Back to those 6 commute times. That's exactly the spot we're in. A handful of readings, no idea of the true average, and no idea of the true spread. With so little data, how wide does the usually it's about range have to be honest?
And here's the subtle thing, and it's the heart of today. Swapping a known sigma for an estimate s adds a second layer of uncertainty. We're now guessing the spread and the center. And that extra wobble actually changes the curve we use.
Changes it to what exactly?
To students t, which we met back in week 3, when you put s in place of sigma, that standardized quantity, x bar minus mu over s over root n, no longer behaves like a standard normal z. It follows a t distribution.
And the t comes with a dial, the degrees of freedom, v, which is n-1. It's still a symmetric bell, but with heavier tails than the normal. Look at the picture. Same center, but the t sits a little lower in the middle and fatter at the edges.
Those fat tails are the price of estimating sigma. They leave extra room for the times our s guessed low. One catch to flag. The t interval assumes the population itself is roughly normal. And as v gets large, big samples, the t quietly turns back into the normal.
Now the interval. Same construction as last time, just with t instead of z.
So we pick the critical value t alpha over 2 at v equals m-1, so that the chance our standardized mean lands between minus it and plus it is 1 minus alpha.
Then it's the same algebra as before. Take that inequality and solve it for mu instead.
And out comes the headline. X bar plus or minus t alpha over 2 times s over root m. That's a 100 times 1 minus alpha % confidence interval for mu when sigma is unknown and the sample is small.
Same shape as a band 2. Mu sits between x bar minus the margin and x bar plus the margin. Literally the z interval from last time with 2 swaps, s for sigma and t for z.
Where does t alpha over 2 actually come from? Table A4?
And it's a 2-dimensional lookup, unlike the normal. For a 100 times 1 minus alpha % interval, you split alpha into 2 tails, then find the cell in the row v equals m-1, and the column alpha over 2.
Let's make that concrete with the example coming up. 95% interval, sample size m equals 7, so v is 6, and the column is 0.025. The cell there reads 2.447.
And you can see it gold in the table. Row 6, column 0.025, 2.447. Notice how the values shrink as you go down a column. More degrees of freedom, less of a tail penalty. Closer to the normal's 1.96.
Let's run it. 7 containers of acid, volumes in liters. 9.8, 10.2, 10.4, 9.8, 10, 10.2, 9.6. We assume the population is roughly normal and want a 95% interval for the mean content.
First, the sample. The mean x bar is 70 over 7, exactly 10. The sample variance works out to 0.08, so s is about 0.283.
Now the margin. M is 7, v is 6, t alpha over 2 is 2.447. So the margin is 2.447 times 0.283 over root 7, about 0.262.
10 plus or minus 0.262 gives the interval 9.74 to 10.26. With 7 readings and no known sigma, that's the honest range for the true mean, and you can see it bracketed around 10 on the right. Now, a shortcut for big samples. Once m is comfortably past 30, the t-curve is basically indistinguishable from the normal. So we just use z with s, and we can even drop the normal population assumption because the central limit theorem carries it.
Let's test a die. 60 rolls, the average outcome is 2.6, sample standard deviation 0.995, 95%, so z is 1.96. The margin is 1.96 times 0.995 over root 60, about 0.252.
2.6 plus or minus that is the interval 2.35 to 2.85. And here's the payoff. A fair die has a mean of 3.5, and 3.5 sits outside that interval. So with 95% confidence, this die looks loaded.
Now, let's switch from averages to proportions. Yes or no questions. What fraction of voters say yes? What fraction of families subscribe?
The estimate is exactly what you'd guess. P hat, the number of successes x over the sample size m, and Q hat is just 1 minus P hat, the fraction of no's.
And does the central limit theorem write in again? It does. P hat minus P over root of PQ over M behaves like a standard normal. So we get a normal-based interval, same family as the mean.
And it has the very same shape. P hat plus or minus z alpha over 2 times the root of P hat Q hat over M. Estimate in the middle, z times a standard error on each side.
One guardrail, though. That normal approximation only works if the sample is big enough. The rule is m times P hat is at least 5, and m times Q hat is at least 5. Too few successes or too few failures, and the bell shape breaks down.
Let's do one. 500 families with TV sets. 340 subscribe to HBO. We want a 95% interval for the true subscriber proportion.
So P hat is 340 over 500. That's 0.68. And Q hat is 0.32. Quick guardrail check. NP hat is 340, and Q hat is 160. Both way past 5. We're good.
Standard error. Root of 0.68 times 0.32 over 500, about 0.021, times z of 1.96 gives a margin of about 0.041.
So 0.68 plus or minus 0.041, the interval 0.639 to 0.721. 68%, give or take 4 points. That is exactly the shape of the poll we opened Lecture 14 with, 47% plus or minus 3. Here's the planner's question, the one a pollster asks before collecting anything. How many people do I need so my margin is small enough?
Run the margin backward. The error is at most z alpha over 2 times the root of P hat Q hat over M. Set that below your target E. Solve for M, and you get m is bigger than z alpha over 2 squared times P hat Q hat over E squared, and always round up.
Say we want to pin HBO's 68% to within 3 points. E equals 0.03. Plug in 1.96 squared times 0.68 times 0.32 over 0.03 squared. That's about 929 families.
And that's why national polls survey around 1,000 people for a plus or minus 3 margin. Want it tighter? The cost climbs fast because m sits under a square root. Halving the margin takes 4 times the data.
Now, let's use this for a real decision, the kind your BMC capstone asks for. Riverbend Community Food Pantry has a hunch. Sending a weekly reminder raises the share of families who actually pick up their box. Is that true?
That's a comparison of 2 proportions, and the interval looks just like the one sample case, only doubled up. The difference P hat 1 minus P hat 2 plus or minus z alpha over 2 times the root of P hat 1 Q hat 1 over M1 plus P hat 2 Q hat 2 over M2. Both groups wobble, added under one root.
And the decision rule is the punchline. If the whole interval sits above 0, the 2 groups genuinely differ. If the interval straddles 0, the data can't confirm any real difference. The gap you saw could just be noise.
Riverbend's numbers. Of 200 reminded families, 150 picked up. That's 0.75. Of 200 not reminded, 120, 0.60. The difference is 0.15. The combined standard error is about 0.046, and z is 1.96, so the margin is about 0.091.
0.15 plus or minus 0.091 gives the interval 0.059 to 0.241. The whole thing clears zero. So with 95% confidence, the reminder really does lift pickup by somewhere between 6 and 24 points. The pantry keeps it. That's statistics defending a decision.
One more parameter, and it's a different flavor. Sometimes the spread itself is the question. How consistent is a process, not where it's centered.
Then S squared is our estimate of sigma squared, and it's unbiased. And for a normal population, the quantity m-1 times S squared over sigma squared follows a chi-squared distribution.
With v equals m-1 degrees of freedom again. But chi-squared isn't a tidy symmetric bell. It lives on the positive side and leans to the right.
Which forces a different looking interval, m-1 times S squared, divided by the chi-squared cutoff on each end. And because the curve is lopsided, those two cutoffs aren't mirror images. The interval for sigma squared is not symmetric. Watch how that plays out next. Because the curve is skewed, we read two different critical values, one for each end.
Take a 95% interval at v equals 4. The right-hand cutoff, chi-squared 0.025, is 11.143. The left-hand cutoff, chi-squared 0.975, is not 0.484.
And the thing that trips everyone up, both of those are area to the right values. 0.975 to the right just means almost everything is to the right, so it's a tiny cutoff near zero. They're not symmetric because the curve isn't.
And the table makes it concrete. Row v equals 4, the 0.975 column gives 0.484, and the 0.025 column gives 11.143. Those two gold cells are the two ends of our interval.
Let's settle a warranty claim. A maker says its batteries last 3 years on average, with a standard deviation of 1 year. 5 batteries last 1.9, 2.4, 3, 3.5, and 4.2 years. At 95%, is sigma equals 1 still believable?
Sample first. The mean is 3. The sum of squared deviations is 3.26, so S squared is 3.26 over 4, not 0.815, and V is 4.
Now the interval. Lower end, 4 times 0.815 over 11.143. Upper end, the same 4 times 0.815, but over 0.484. That gives sigma squared between 0.293 and 6.737.
And the verdict. The claim is sigma equals 1, so sigma squared equals 1. And 1 lands comfortably inside that interval, so there's no reason to doubt the maker. Notice how wide the interval is, though. 5 data points just can't pin a variance down tightly.
Quick practical note before we wrap. If you'd rather not hunt through tables, GeoGebra's free probability calculator gives these critical values straight. Pick student T, set the degrees of freedom to 6, set the central probability to 0.95, and it shades the middle and reads the cutoffs at plus and minus 2.447, the same T.025 from the acid example. Switch it to chi-squared with V equals 4, and it hands you the two skewed cutoffs, 0.484 and 11.143, for the battery interval. Same numbers, no table.
Let's gather it up. Today we built confidence intervals for when sigma is unknown, the T interval for a small sample mean, and Z with S for a large sample.
Plus an interval for a proportion, and a two-group comparison that let Riverbend make an actual call, and the chi-squared interval for a variance. But notice what every one of these did. It estimated an unknown. What if instead somebody hands you a claim, the average wait is 5 minutes, and you want to know if it's true?
That's the whole next chapter. Lecture 16, Hypothesis Testing. We state the claim against an alternative, build a test statistic, and read the p-value as evidence, not a verdict. We've actually been doing it already today, every time we asked whether a value fell inside an interval or outside it. Next time we make it official. See you there.